Hi, welcome to this video in the uTasker Shorts series. Today we're going to be looking at the flash protection offered in the KINETIS parts. To get the ball rolling, I've connected a KINETIS board to my computer via a terminal emulator. This is a 1 megabyte device running the uTasker project. Now the uTasker project always gives you a command line shell with various useful commands, including I/O memory. In the I/O memory, I'm going to do a memory display of a part of the flash. I'm looking at 48 bytes. Now the reason why I'm doing this is because I want to look at the contents of the so-called flash configuration. Now the flash configuration are 16 bytes which are programmed in flash, and each time that the processor resets, these values are loaded into internal registers. Now what I have here is a representation of what we've seen. First of all, the 8 bytes at the beginning represent so-called backdoor keys. Now we're not going to discuss these today because they don't have anything to do with the actual flash area protection. The flash area protection are these 4 bytes which are located here, followed by a security byte, an option byte, and in some chips further bytes to control EEPROM protection and also data flash protection. After each reset, these protection bytes are loaded into internal registers called fprot3 to 0. Each of the bits in these registers then controls the access to flash. For example, if we leave everything at F, each of the flash areas which can be protected are not blocked in any way from erase or programming. The actual area is always divided into 32 sections, one section for each of these bits, which means that if we have a 1 megabyte flash part, we have a flash protection granularity of 32K. Now notice the bits. This bit here protects this one. This bit here protects this one. It's a little bit weird. The reason is because basically this is a big endian design on a little endian chip. So if we go and now look at the setup in the uTasker project, we'll see that it actually makes more sense if we work with long words, because long words then actually orders the bytes or the bits and also the protection bits themselves into a nice orderly sequence. So now let's see it in practice. I'm getting my terminal emulator back up, and now I'm going to use some storage modify commands. Now these commands actually let me read, write, erase flash. So what I'm going to do is I'm going to try to write a bit of code or a bit of data into the final section in flash, and then we'll protect it and we'll see whether we can erase it. Now to do this, I use the sector fill command. I give it my address. I say I want to write bytes. Let's say I'm going to write an AB and I'm going to write it 16 times. I'm going to check that that worked. Now here we can see that I actually I did a memory fill into flash. I wrote some bytes. Now normally I would expect to be able to erase this, but what I'm going to do is I'm going to modify this register here, and I'm going to try to protect it. Now I know that the actual flash protection register has this address. I'm going to access it as a byte first of all, and we see that we have FF because I've got no flash protection set up in my actual flash configuration area, but I'm going to modify this now because I'm allowed to modify it. Byte. I'm going to protect the final bit, which means if I write a 7F, let's check that. Now I've got one bit at 0. Now theoretically, if all of this works, I've now protected this area in flash. So let's see whether I can erase it. I'm going to do a sector erase, or storage erase actually. F8000. I'll give it a length of 0. That just means the smallest possible size. What happens? I had a failure. Let's check it. Yes, it's all at the same value. So what I can do now is I can do a check of the flash controller status register to see what actually happened, because we did try to erase it. Now I know that it has this address, so I'm going to check. It's got a value of 90. The 10 in there is telling me that there was a flash protection error. I couldn't write it because it's protected, so I'm going to do a reset of my board now. It's coming back up again. Get back into my memory. I'm going to check that my flash still has the same value as before, which it does, and now I'm going to do a sector erase of it again. It said it's erased. Okay, let's check it. Yes, it's fine. So what does this teach us? It means that even if we don't have the flash protection out of reset, we can still add it. Sounds good. So how do we remove the protection? Let's see. I've got no protection. Let's add it. I'm protecting the final one again, just checking it. Alright, so we know that that would work now. I couldn't write, I couldn't erase. But let's say I've changed my mind. So what do? I go and take my memory modify and I set it back to FF. Great. Got no flash protection. Check. Oh. Well, this tells us now, if I set flash protection, I cannot get rid of it. It's stuck. The only way to get rid of it is to do a reset. To explain this behavior, we read the description of the F protection bytes. And it says here, in non-volatile memory normal mode, all bits with 1 to 0 transitions are ignored. Now we've already realized that that's the case. So how could we get around this? Well, the only possibility is to set the switch into NVM special mode. Now unfortunately the program cannot do that itself. This can only be done by using the EZ port. So now we can conclude. We've seen the flash protection in operation. We've seen that it can be set by the flash configuration. We've also seen that it can be actually increased in level by the program itself by writing to the registers. However, once you have flash protection on a sector or a protection granularity area, it cannot be removed without removing it by using a programmer or by making a reset when it was set only by the program. I hope you enjoyed this video. If there are any questions, just ask them. If you want to develop faster, get uTasker, as simple as that.